This video is on the objective conduct and interpret a test of independence with the chi-square distribution. So again, we're running here a chi-square, test for independence, meaning we're trying to determine if two variables or two factors are independent or not. Alright, so let's take a look. And if you want to see more about the topic, please click on More Instruction. And they have some videos, or read their examples, their notes, and hopefully those help you out. In fact, I'm just going to go over some of it here, so I don't have to write it down. So if we're conducting a chi-square independence test, right, as I mentioned, in this type of hypothesis test, you determine whether two factors or two variables are independent or not. These steps look very similar to other types of hypothesis testing, right? You set up your hypotheses, determine your significance level, compute the test statistic, then find critical value, and set up a rejection region and all that. So very similar. However, the main differences are the null and alternative hypotheses, which are the same for all independence tests. Right. So any of these tests for independence, the null hypothesis and alternative hypothesis will be the same statement every time. Note, the expected values for all factors must be greater than 5 in order for this test to be conclusive. Alright, so why that is, we're not going to get into that. Just keep a note of that. Alright, so the steps of completing a chi-square independence test. So the first is, as usual, record the hypotheses. Again, here for every independence test, we're going to have the same hypotheses. The null hypothesis is that the two variables are not associated, meaning they are independent. All right, so we're going to be assuming that the variables are independent and then deciding whether or not to reject that. The alternative hypothesis is that the variables are associated, therefore they are dependent. Number 2, right, you have decide on the significance level, right, that value of alpha. Number 3, compute the test statistic, that chi-squared sub 0 or chi-squared test, using the expected frequencies, and they have remember the formula for it down here. This is actually written out in a weird way. Just remember you're taking all the observed values minus their corresponding expected values, squaring those, and dividing by the corresponding expected values, and you're going to be adding those up for every cell of your contingency table. I'll just show you, use a calculator, right? Because this can take a while if you're doing it by hand. I'll show you both, but you'll definitely see the calculator is better. There's a shortcut. Determine the degrees of freedom. Right, to find the critical for our chi-square distribution, and then from that you can determine the critical value. Which chi-square value has an area of alpha to the right. And these are always going to be right-tailed tests. These tests for independence. And then you decide if you reject or fail to reject the null, and make a conclusion. Are we going to conclude at the significance level alpha that the variables are independent or not? Right. So I mentioned the test statistic. Now the degrees of freedom. Remember, for a goodness of fit test, it was the number of categories minus 1. Here it's calculated in a bit different way. The degrees of freedom are found by using the formula, r minus 1 times c minus 1, where again, r minus 1 is the number of rows in the table minus 1 in the contingency table, and c minus 1 will be the number of columns minus 1. All right, so it's like the number of categories for the row variable, minus 1, times the number of categories for the column variable, minus 1. This will be the degrees of freedom for our chi-square distribution. The independence test is always right-tailed. If the expected and observed values are not close together, then the test statistic will be very large and way out in the right tail, and we would, just like in a goodness of fit test, and we'll probably reject independence there. We'll reject the null hypothesis. And if the expected values and observed values are really close, then we'll fail to reject. It all depends on the value of alpha and the number of degrees of freedom, right, where this rejection region will be. All right, so they give you an example here. I'll let you read that on your own. Let's go to our problem. All right, so question, does favorite food depend on your gender? So favorite food and gender are two variables here, two factors, and we're asking, are they dependent or independent of one another? So a survey asks a group of college students about their favorite foods. It also groups the students by their gender. The data are recorded in the contingency table below, and a chi-square test of independence at the 5% significance level is performed. So that's alpha. All right, so I'm going to write this table out, and we're going to set up the hypotheses and all that stuff. So here's the actual observed values. Now I didn't put the totals in yet because this is the table we're going to focus on. Now, the number of rows, that lowercase r they mentioned right there, so there are 2 rows. And the number of columns, that lowercase c I mentioned earlier, is 3 columns for the foods. Right? So we have a 2-row by 3-column matrix here, and you're going to see me enter a matrix into my calculator later. All right, and then some important numbers for us are going to be these totals. Right, so across the bottom here, we'll add up the columns. Right, so these will be the column totals, and I'm doing these in a different color because they aren't actually part of the main table. So how many of these students that were surveyed have sushi as their favorite food? That's 33. How many have pizza as their favorite food? 16. How many have hamburgers as their favorite food? 33 again. Right. And then over here in this extended part here, again, this is in a different color because it's really, again, not part of the main table, are row totals. Right. So how many of these students identified as male? It's 25 plus 19 would be 44. And how many of these students that were surveyed identified as female? It's 38. Right? Just 21 plus 9 plus 8. Right? And then in the lower right corner is the total number of students that were surveyed. Right? So in this lower right corner is just the total number of students that were surveyed. So 44 plus 38 is 82. And you can call this like lowercase n or something for the sample size, right? And this would be the same as if you took 33 and 16 and 33, right? This adds up to 82 as well. But here's your sample size, right? How many students were surveyed here? Okay. Again, different color because again, it's not part of the main 2x3 table. All right. So we're testing whether or not favorite food and gender are independent, right? Do they have some sort of association or not? So the hypotheses, right, again, I've mentioned this before, the hypotheses will be the same for all these tests for independence. So the null hypothesis is that a student's favorite food and their gender are independent. They have no association. Right. And this is what's going to be assumed, right? So we're going to assume they have nothing to do with each other. There's no association. They are independent. And the alternative hypothesis is that the favorite food of a student and their gender are related in some way. They are dependent. Okay. All right, and then you have alpha, right? The second step is usually identifying the significance level, and they told us, we're going to be doing this test at a 5% significance level. So alpha is 0.05, right? So this is the beginning of this, right? So the hypotheses, the null hypothesis is that the two variables are independent, right? So gender does not have an effect on favorite food. And the alternative hypothesis is that they are dependent, so gender does have an effect on favorite food. So again, simple start. All right, next. Next we're asked to compute the test statistic and round to 1 decimal place. Now they ask us to also use expected frequencies that are also rounded to 1 decimal place. Alright, so this is where things can get a bit hairy. Alright, and let me show you, because if you round all these values to 1 decimal place and then round the final answer to 1 decimal place, you're doing a lot of rounding. So your final answer, is not going to be exactly what a calculator would give you. And I'll show you the difference. I will show you the difference. Alright, so first I want to go back to my paper here and talk about those expected frequencies. We'll make a table of expected frequencies. Now, if you recall, hopefully you saw my videos. If not, go look at those now if you want. But there was another objective where you were asked to calculate the test statistic for a test for independence. And those expected frequencies were calculated for each cell, and there are 6 cells here in the contingency table. And here's how they're calculated. And I went over this in another video, how this formula came up. So the expected frequency for the ith row jth column cell, this is expected frequency for the ith row jth column, I comma j here. It's Ri times Cj divided by n, where this Ri is the ith row total, the total of the ith row, which we're seeing in the row totals. This Cj is the column total for column j, right? And the column totals I have in red here. And then again, this lowercase n is the whole sample size, which in this case is going to be 82. All right, so I'm going to do on this page, and then I'll just write it in the same table but in a different color, is the expected frequencies. Right, so the expected frequency for the first row, first column, that's males that have sushi as their favorite food, would be the row 1 total, which is 44, multiplied by the column 1 total. So again, I'm in row 1, column 1. So row 1 total times column 1 total divided by the total sample size, right, divided by 82. And again, they're asking us to use these expected values rounded to 1 decimal place. All right, so I have my calculator up, and I'm going 44 times 33 divided by 82, and round it to 1 decimal place. This would be 17.7. All right, and I'll write that in this light green color. So again, I'll put the approximately 17.7 for the expected value. So the observed value is 12. The expected value is 17.7. Alright, and then the expected count or expected frequency for the first row, second column, so males who prefer pizza, would be, again, the row 1 total times the column 2 total. So again, I'm here now, 44 times 16, and again divided by 82. And we're going to round this to 1 decimal place. Now the nice thing is I can just go second entry and change the 33 there to a 16. And it's approximately 8.6. Alright, 8.6. So again, with this color, approximately 8.6. Again, the observed value is 7. The expected value is 8.6. And I'm just going to do the same thing for the rest of these, but without writing them down. So here, first row, third column, I'm taking 44 times 33 divided by 82. Well, I did that already. That's 17.7. Alright, 44 times 33 divided by 82. Now, if I'm here with the females who prefer sushi cell, I'm going to do 38 times 33 divided by 82. So 38 times 33, nope, come on, 33 divided by 82. So that's approximately 15.3 for the expected frequency there. Then for first row, second column, and the females who prefer pizza, 38 times 16. So I'm just going to change that 33 to a 16. Times 38 times 16 divided by 82, so approximately 7.4. And finally, in this second row, third column, 38 times 33 divided by 82, which again I already did, and that's this calculation here: 38 times 33 divided by 82. So the expected count here is also approximately 15.3. All right, so I've got all the observed counts, and I also have all the expected counts. So now the test statistic using those values. All right. Remember the test statistic for a chi-squared test, and this was the same for a goodness of fit test as well. The test statistic for these chi-square tests, chi-squared sub 0 is the sum of all the observed values minus their corresponding expected values squared divided by that corresponding expected value. And there's, one for each cell. So I'm going to be taking, there will be 6 of these. All right, and I'll type this in my calculator, but we're taking, for the first row, first column, the observed count was 12 minus the expected count is 17.7. This is being squared and divided by 17.7 plus, and then I do it for the next cell, first row, second column. Observed 7 minus the expected 8.6 squared divided by 8.6 plus, same for the first row, third column, 25 minus 17.7, that quantity squared divided by 17.7 plus, do it for now for this cell, second row, first column, 21 minus 15.3, that quantity squared divided by 15.3 plus, then second row, second column, 9 minus 7.4 squared divided by 7.4. And then finally, the second row, third column here, 8 minus 15.3 squared divided by 15.3. And then they're asking us to use these rounded to 1 decimal place expected values, punch all this in, and round the final answer also to 1 decimal place. All right, so let's start typing this in. So I got 12 minus 17.7. Well, actually, you know what I'm going to do instead is what I did with the goodness of fit test to speed this up maybe a little bit. Enter these as lists. If I go stat, edit, go down list 1, I'll enter these observed values. You had 12, 7, 25, and then down the second row you got 21, 9, and 8. Alright, and then down list L2 I'll enter all the expected values, 17.7. And then make sure that they're lined up with the correct observed value, right? 12 with 17.7, 7 with 8.6, and so on. 8.6, then 17.7 again, and 15.3. And after I'm done with all this, I'm going to show you a much faster way to find all these things. 7.4, 15.3. Okay. And now that those are all lined up, right, every observed value with its corresponding expected count, I go over to another list, an empty list like L3, move my cursor up to L3, and then enter this expression here, observed minus expected squared divided by expected. So the observed counts are all in L1, minus the expected counts are all in L2. Square these, divided by the expected counts again, L2. And then the test statistic is going to be the sum of all 6 of these values in this third list. So let's get out of here and find the sum of the values in a list. That was above the stat button. You go to list, over to math, and I want to find the sum of the values in list L3. Right. And they're 11.096, which would round to 11.1. So there's the test statistic, that, the way they wanted us to find it. Right, the way they wanted us to find it. All right, so back here I'm going to enter, 11.1. Okay. Again, that was using all those expected counts rounded to 1 decimal place. Now, let me show you a faster way to do this, but it might not be the exact same value because they're not rounding. The calculator is more accurate than this. So here's a much quicker way, though, to calculate. If you weren't asked to round everything to 1 decimal place. Now here would be also a quicker way to find the expected values, instead of doing all that typing I did earlier. So let me pull up the calculator again. And remember, this table has 2 rows and 3 columns. And I mentioned earlier, I'm going to put together a matrix on the calculator. Above the x to the -1 button, there's should say matrix for TI 83s and 84s. If I hit second and go to this matrix menu, then go over to edit, I can make a matrix. I can make my table basically. Hit enter. Now on the top here it asks you to fill in the number of rows by the number of columns. So this is the 2 rows, enter, by 3 columns. And then you see it's got these 6 zeros to replace here, these 6 spaces. So I'm just going to put in the table as is. The first row, first column is the men who prefer sushi. There were 12 of those. I'm just going to put in the observed counts. I'm going to go back to the original, just enter these observed counts from the original table. Then we had 7 men who preferred pizza, 25 who preferred hamburgers, and then the females, 21 who preferred sushi, 9 who preferred pizza, and 8 who preferred burgers. Right, so I enter this matrix, quit, get out of here, and then to get the test statistic, again, it's going to be a more accurate test statistic. To get the test statistic, we're going to run a chi-squared test on the calculator. Hit stat, hit the stat button, go over to tests, and then scroll down until you see chi-squared test, which is, I think, is at C. Right, there it is. Chi-squared test. And then it'll ask you, what are your observed values? What's the table? What's the matrix? And that was matrix A that I entered. Now, if you want to enter a different matrix, you go second matrix, and then go down the names here and enter whatever matrix. Now, we already had it at matrix A. All right. Now, we didn't enter an expected matrix, and it doesn't matter. It's going to make it for us. All right. If your observed matrix is entered correctly and you just go down to calculate, look at this. Now, this would still round to 11.1, so you'd be good. All right, you'd be great. We got lucky. Sometimes when you round a lot, the last answer isn't as accurate, but here this would round to 11.1. So even if I just use this calculator, I would have gotten 11.1, entered that, and it would have been correct. And I'd say more often than not, this will be correct when rounded to one decimal place. It'll be the same as if you do all the rounding. Just in some cases, it may be a little off. And it also gives you a p-value for the test, and you can compare this to alpha later and decide whether or not to reject the null hypothesis. I'll get back to that too. It also gives you the degrees of freedom. Right? Now, the most important of these is going to be the p-value, right? Because then you'll use that to decide if you're going to reject the null. But the test statistic is 11.1. But aside from this, go back to that matrix menu. Look at this. See how now there's a matrix B? Enter matrix B on the main screen. Look, 17.7, 15.3. Scroll over, you got 8.5, 8.6, 7.4 in the second column, and then the third column, you got 17.7, 15.3 again. These are your expected counts. It made it for me. All right. Yeah. So that's how you can use a calculator, and just simply entering a matrix with your observed values. That's all you need to do to run this test. All right, so we got the test statistic, and then they're going to ask us for a critical value and degrees of freedom and all this stuff. Right. So, now, so we got the hypothesis set up. We have our test statistic. Now we're asked to use this table to determine a critical value for this test. All right, so back to my paper. Back to the paper. So it was mentioned earlier, right, the number of degrees of freedom for the chi-squared test was the number of rows minus 1 multiplied by the number of columns minus 1. So for this table, right, there were 2 rows, there were 3 columns. So this is just 1 times 2. So we're looking at the chi-squared distribution with 2 degrees of freedom. And I'll draw a little picture of that. So again, your horizontal axis is different values of this chi-squared. And with 2, and it starts at 0, never goes negative, and it's skewed left. Now this one was kind of like a sloping down deal like that. It wasn't. It maybe like that, but bulky on the left, gets low on the right. It's skewed right, skewed right. And remember, the mean would be the number of degrees of freedom. The mean is 2, which is to the right of the peak, and so here's the mean value, and the standard deviation would also be 2. Right? Remember, it was the square root of 2 times the degrees of freedom. So here it would be the square root of 4. And what we're looking for is, what's the value of chi-squared with an area of alpha to the right. Now alpha here, we said earlier, was 5%. That's this area, the rejection region. So we're looking for chi-squared with 5% to the right of it. All right, and it's always a right-tailed test, these. Well, let's see what that is from our table. All right, so back here, looking at the 2 degrees of freedom row. All right, looking at the 2 degrees of freedom row. and I'm looking for the chi-squared value with, alpha to the right, 0.05, 5% to the right, that'd be 5.991. I'm looking at this value right here. Right. 5.991. So back on my paper, right, this value is 5.991, and then we have to determine, do we reject or fail to reject the null hypothesis? Now remember, our test statistic was 11.1, which is definitely in the rejection region. All right, here was our test statistic. Definitely in the rejection region. So I would reject the null hypothesis. Right? I'd reject independence. And if we go back to our hypotheses, right, we're going to reject this. So we're not going to say that, favorite food and gender are independent. We're going to say that, our evidence supports the statement that favorite food and gender are dependent, right? They are related or associated in some way. And that'll be our final conclusion. All right, but for right now, we're asked for this critical value, right? 5.991. So 5.991 from that table. Okay. And then I'm sure finally it'll be like, now what's your decision? What conclusions can be made? Again, we would reject the null hypothesis because our test statistic is clearly in the rejection region. You could have also used the p-value method. Right? Remember the p-value, let me pull up my paper. The p-value being a right-tailed test, the p-value would be the area to the right of the test statistic. And the p-value is actually given to us from the calculator when we run that chi-squared test with that matrix of observed values, right? It goes stat, tests again, just down to C. Get the chi-squared test. The observed matrix is still the same. And, again, the test statistic, now p-value is 0.003, 0.004, right? If I round to 3 decimal places. This p-value is definitely less than or equal to alpha. Right? The p-value is less than 5%. So again, I would say reject the null. Whether you're using the critical value approach or the p-value approach, you're going to reject the null hypothesis. All right, and if you reject the null hypothesis, that means we're not saying they're independent. We're going to say they're dependent at this 5% significance level. So let's see. At the 5% significance level, there is not enough evidence to conclude that gender affects favorite food. No, there is. We're saying that gender does affect favorite food. Right? They are dependent. So I'm saying this last one. Okay, great. And again, like most of these objectives where you have to complete the steps of a hypothesis test, if you go through it all and get it all right the first time, take your time, that should be the only question you're given in that objective. The objective should be over, which is nice. All right, now if you get something wrong in there, it's going to make it longer, and you'll have to maybe do another question. But still, shouldn't be too much with these objectives. Okay, so again, hopefully watching me go through this, using the calculator, drawing it on paper, looking at the more instruction, their videos, their examples, their notes, reading the answer explanations when they come up. I'm hoping all this stuff helps you out when you're trying to do this on your own. And thank you very much for watching.